Hello everyone. Today we are going to talk about complex numbers. Okay, I assume that you have seen or will see complex numbers in some parts of your formal education in undergrad, but per my experience, I found that typically complex numbers for many engineering bachelor students is offered as an elective math course, and so many of them do not really have to take it or do not include it in their 4 year plans. And so when they graduate, they do not have a proper knowledge of complex numbers. They might see a brief intro to it, maybe in differential equations or something, but as they go to higher level courses like controls, maybe vibrations, advanced electric circuits, and so on, they see more and more of complex numbers. And I decided to devote 1 or 2 lectures to complex numbers and provide a little bit more info on this topic. So here I start from scratch, assuming that you don't know much. I start from scratch, although some of you, as I said, might know it. So if any of this material in the beginning are not new to you, you can move forward in the video. So the idea of complex number started with, can I solve this simple quadratic equation that x squared plus 1 equals 0? We know if x is a real number, there is no solution here, right? Such that x squared is actually equal to -1. There is no such solution. And so, the solution will be x equals plus or minus square root of -1. And we don't know any solution in real numbers for it. That's where the complex numbers come in. And complex numbers basically are imaginary numbers. They are not something that exists in the real world. We don't have any quantity that has such amount that when you square it and add 1 to it, you get a 0. Okay, so these are imaginary numbers, and that's where they introduced a term I or J, the base of complex numbers, and they call this I. Electric students, they use J instead of I for this, and the reason for them is they use I for electric current. Okay, so they either call it I or J in math. As I said again, electric students call it J. And so they said there is this imaginary number I or J such that what? Such that I squared is equal to -1. So the solution was plus or minus I. Okay? So again, this I is completely imaginary. There is no such thing in real life. But by creating these imaginary numbers, it helped them solve many problems in engineering in a nice way and in a more convenient way. And I'll tell you, when we get to the Euler equation, I'll tell you one example where this guy is really useful. Okay? So then they said, like, complex numbers are like 2D versions of real numbers. So if the real number, you imagine what we had in real numbers were one axis, correct? That was the real axis. And it goes to positive infinity, negative infinity. Somewhere here is 0. Now they said, why don't we add a secondary axis that is perpendicular to this real axis? It also goes from negative infinity to positive infinity. But this axis, we call it the imaginary axis. So IM means imaginary. RE means real. Okay? So they said now this axis will be basically showing how many i's or how many j's that complex number has, and this real part shows the real portion. So when, for example, I have a point here in this complex plane, it might have, let's say, 2 units of real, positive 2, and it might have positive 1 in the imaginary axis. Therefore, if I want to show that point with a complex number z, that number is going to be 2 plus 1 times I. Okay, that is this complex number, 2 plus 1 times I. Good. So basically you can treat them like vectors, correct? Like vectors that we had basically x and y components, you can treat complex numbers like vectors. They have real component and they have imaginary component again, right? So here we say this 2 is the real part of z, and this 1, positive 1 and positive 2, this is the imaginary part of z. Okay, like the x and y component, basically, it's similar. And now we define addition, subtraction, division, multiplication, power, and everything for this new set of numbers, all based on this initial definition. Everything comes from this definition, that I squared is equal to negative 1. Everything comes down to this guy. Okay, so for example, when I want to add number z1, which is like a plus b times I, a is the real part, b is the imaginary part, and I have z2, which is like c plus d times I, then addition and subtraction is very easy. So z1 plus or minus z2 means what? Means add their real components together. So this is going to be a plus or minus c, and then add or subtract their imaginary components. So it is going to be b plus or minus d times I, right? So you see, very simple. Just like when you add two vectors together, you add their x components and you add their y components, right? That's the same thing. Add reals together, add imaginaries together, or subtract. So addition and subtraction is very simple. Now, when you multiply these two complex numbers together, z1 times z2, here you have to use the distributive property of product with respect to addition. So each one of them is one term. A is one term, bi is one term, c is one, di is one. So 2, 2, you have 4 terms. And you will get what? You will get ac plus ADI plus C times BI, and then plus B times D times I squared, correct? And now you use the definition that I squared is equal to negative 1. So this term now becomes real. It's negative BD. This term is real. That's positive AC. So these two terms in blue are real. And these two terms underlined with red, they have I in them, so they are imaginary. So if you now want to simplify it, it is going to be what? It is going to be AC minus PD, that's the real portion of this result, plus what? D plus BC times I. Okay? So that is the product of two complex numbers. And now, before I talk about the division, I need to introduce one new notion in complex numbers, which is called complex conjugate. So the complex conjugate for a complex number is basically The same as the complex number for the real component, the imaginary component of that is negated. So you will get here. The real component is positive 2. The imaginary component is negative 1. And this guy, I call it z bar, which is 2 minus 1 times I. And again, I call this complex conjugate of z. Okay, so if you just negate the imaginary part of a complex number, you will get its complex conjugate. What's the use of that? I'll tell you right now. But just this is a new definition I want you to know. So now, let's say I'm about to divide two complex numbers. So it is going to be z1 over z2. What does it mean? It means a plus bi divided by c plus di. Right? Now, I want to write the result of this as one real number plus another imaginary number times I, or imaginary number times imaginary I, basically. But right now, it is not in that form. So what I will do, I will multiply both numerator and denominator. I will multiply both numerator and denominator by the complex conjugate of the denominator, which is c minus di. This is like I'm doing nothing, right? Because these two can be canceled. Okay, now what's the good thing about it? The good thing is in the denominator. When you multiply a complex number by its conjugate, what would you get? So before I get to this part, I would like to show you here that, for example, when I multiply z1 by z1 conjugate, what do I get? Well, it is going to be a plus bi times a minus bi, right? And if I follow this formula, where C is the same as A, D is the same as B, correct? Sorry, D is the same as negative B, C is the same as A. So it is going to be A squared plus B squared, and this term is going to be negative AB plus positive AB, it's going to become 0. So the result is going to simply be a squared plus b squared. Now, what is a squared plus b squared? Clearly, it is a pure real number. There is no I in it, okay? It's pure real, okay? That's the good thing. Also, here, I have to define two new terms for you. And those are the magnitude or absolute value of the complex number and the argument or the angle of the complex number. So some new definition for you. The magnitude of the complex number is equal to just the length of the vector, which is simply what? The square root of the real part squared plus what? The imaginary part squared. As simple as that. This is called the magnitude or absolute value. And then the angle here, if we call this angle theta, which is measured from the real axis in a counterclockwise manner, then this theta, which we also call the argument of z, or some textbooks show it with something like this. The angle of z, This is clearly tangent inverse of the imaginary part of z over the real part of z. Okay, so two new definitions, magnitude and angle of the complex number. So clearly, in this case, a squared plus b squared is the same as what? Is the same as this square root to the power 2. And this square root is the real part of the squared plus imaginary part of the square. So it is going to be the magnitude of z1 squared. Okay, so when you multiply any complex number by its conjugate, the result is simply a single real number, and that is the magnitude of that complex number. So here, when I'm dividing, what do I get? When I'm dividing, by multiplying both numerator and denominator by the conjugate of denominator, what I will get is the product of these two over the product of these two. But the product of the two terms in the denominator, since they are complex number and is conjugate, is going to be c squared plus d squared, which is a pure real number. Now the numerator, you have the product, and if you follow the top rule, you will see that what? You will get AC plus BI times negative DI, which is going to be negative BDI squared, and I squared is -1, so that -1 with this negative cancels. And so if you simplify, you will get AC plus BD for the real portion, and then plus, it is going to be negative AD plus BC with the I. Okay, and now you can divide and get one single real number, where the real part is AC plus BD divided by C squared plus D squared. That's the real portion of the number, plus the imaginary portion is BC minus A times D divided by C squared plus D squared, the whole thing times I. Okay, so this is how you divide the two complex numbers. This is how you add or subtract. This is how you multiply. And this is the result of product of a complex number by its conjugate, which is simply a real number. Okay, so far we had some basic definitions. And now it is time to take it to the next level. Okay, so what can we do to take it to the next level? So let me first see if I can expand this a little bit. That's good. Okay, so this is the basic arithmetic of complex numbers. The basic definitions, basic arithmetic. Now, there is one very important formula in complex numbers called Euler number. But before that, I want to tell you a couple of more things about conjugate and then talk about this Euler formula. So some properties of this conjugate are like this. If I conjugate z and then conjugate the result of the whole thing, of course, the result is going to be back to be the original z. No problem. If I add or subtract z1 and z2 and then conjugate the whole thing, it is like conjugate of the first one plus minus conjugate of the second one. So the conjugate is distributed over the plus or minus. The same thing goes for product and division. If I multiply and conjugate the whole thing, it's like the product of the conjugates. And if I divide and conjugate the whole thing, that is like conjugate first and then divide. Okay, so these are some important properties of conjugate. Just wanted you to know about them. Good. So basics. Now we talk about the important thing called the Euler formula. So what is this one? So this one says exponential of I times theta, I is that complex number, is equal to cosine of theta plus I times sine of theta. And you might say, where does that come from? What does exponential have to do with cosine and sine, and how come this power I is now come down and written as the multiple of sine? Well, this is easily provable if you use the Maclaurin series for sine, cosine, and exponential. If you know, based on your knowledge from Maclaurin series and Taylor series, if you don't know them, please watch my video on Taylor series. The Maclaurin series for sine of theta is theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial, and it keeps going. Also, for function cosine of theta, it is 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial, and then keep going. Okay, so that's also what we know. You also know for the exponential function that e to the theta is equal to 1 plus theta plus theta squared over 2 factorial plus theta cubed over 3 factorial plus theta to the 4 over 4 factorial, and keep going. Yes? So that's the exponential of theta. Now, if what I do is, instead of exponential of theta, I change this argument theta everywhere with I times theta. So the input argument of the function e to the theta, instead of theta, I make it I times theta. Then here, I expect anytime I have I theta, it becomes, I have theta, it becomes I theta. Correct? So now you have to do a little bit of modification. So this I theta has to be squared and then divided by 2 factorial. Here it has to be to the power 3 divided by 3 factorial. Here it has to be raised to the power 4 over 4 factorial, and so on. Correct? So that's what e to the I theta is, based on the Maclaurin series. Good, now let's expand this term, see what you get. So it is going to be 1 plus I theta stays fine. Here it is going to be I squared theta squared over 2 factorial. This is going to be I cubed theta cubed over 3 factorial. This is going to be plus I to the 4 times theta to the 4 over 4 factorial, and keep going. Now, what are these powers of I? Clearly, power 1 of I is I. I squared, we know, based on definition, it is -1. What about power 3 and 4 of I? Well, if we go back to the definition of I, it's not hard to do that, right? Because I squared is what? -1, right? So what is I cubed? Well, I cubed means I times I squared. And since I squared is -1, so this is going to be equal to I. So I cubed is the same as -I. What about I to the 4? Well, I to the 4 is I squared times I squared. And they are both -1 each. So it is going to be +1. And the same. If you keep going in general, you can show that this pattern would repeat. That you have I to the 1, which is I. You have I to the 2, which is -1. You have I to the 3, which is -I, and you have I to the 4, which is +1. And now if you go to the 5, 5 is I to the 4, which is 1, times I to the 1, which is this. And so this is going to be the pattern that you will see. Okay, right? This is for a power of I, which is like 4k plus 1. This is 4k plus 2. This is 4k plus 3. This is 4k plus 4. Okay, in general. And so here, if you look, this is going to be -I. This is going to be +1. So now if you look, some of these terms are real. Some of them are imaginary. This is real, this is real, this is real. And on the other hand, this guy is imaginary, this guy is imaginary, and probably the next term here, not probably, definitely, the power 5 is imaginary. Therefore, if I factor out the real and the imaginary part, the real part is going to be 1 minus theta squared over 2 factorial, and then plus theta to the 4 over 4 factorial, and ... and the imaginary part is going to be theta minus theta cubed over 3 factorial, and keep going. And guess what? If you look at these, this real portion is clearly the cosine function, and the imaginary portion is clearly what? The sine function. Therefore, exponential of I theta is cosine theta plus I times sine theta. And this very important formula is one of the most formulas that you will use when you're dealing with complex numbers. Okay, extremely important. And based on this formula, I've seen many mathematicians, they come and they write this formula. They say, what is e to the I pi? Well, let's do it. Based on what you know, it is going to be cosine of pi plus I times sine of pi. And Sine of pi is 0, cosine of pi is -1. So the result is -1. And if you bring this -1 to the other side, you will get this equation that e to the I pi plus 1 is equal to 0. And mathematicians love this formula. I've seen many of them call this the most beautiful math formula out there. Because there is Euler number in it, there is pi in it, there is the base of complex number, and there is 1 and 0. So all of those important guys in math are all in one formula. So they love this formula, okay? I tell you that. Okay, so far, these are some very important things that you need to know. Good. Now, let's talk about some other things. So, if I go back a little bit and look at this addition, subtraction, and product and everything, one question I have is, can you change the order here? Instead of z1 plus z2, you make it z2 plus z1. Of course, no worries. Addition, you can easily change. What about the product? Is z1, z2 the same as z2, z1? Well, if you put that here, you see that if you change the order, then this guy, let's just look at it, and then we come back. So what is z2 times z1 if z1 and z2 are defined based on that definition? One of them is a plus bi, the other one is c plus di. So you have c plus di times a plus bi. And if you do that, the result is going to be ca minus bd plus I times CB plus AD. So this is Z2 times Z1. What was Z1 times Z2? It was this guy. Of course, not that big, but can definitely resize it. So now I ask you to look. Are they the same thing? And if you see, yes, they are. Correct? The order are changed, but the result is the same. So that's very important that Z1 times Z2 is the same as Z2 times Z1. So product does have the commutative property for complex numbers. You know, when you're dealing with matrices, you don't have such a thing. But complex numbers, no worries. Okay, you can change the order, and as you can see, there is no problem here. Okay. What about the division? Does it have the same thing? So if you divide Z2 by Z1, of course that should not be the same as Z1 over Z2. Of course not. So you don't expect the division to have such a thing, and you don't expect subtraction to have commutative property, but definitely the product does, and definitely what? The addition does. And these are very important. Okay, so these two properties have the commutative law. What about the distributive? So if you say Z1 times Z2 plus Z3, or minus z3. Can you write it as z1, z2 plus and minus z1 times z3? Yes, you can. Absolutely. Or what about z1 plus z2 plus z3? Can you change the order and say z1 plus z2 and then the result plus z3? We call it associative property. Sure. Okay, so you see you have this important properties. Okay, so if you remember, this guy was called the commutative property. This guy was called the distributive property. Here, product with respect to addition and subtraction. And this guy is called the associative property. So yes, complex numbers show all of these important properties that you need. Now it has a specific name when a group basically qualifies for these properties, but I don't want to make this pure theoretic class. I want to now show you where these complex numbers have any role in real life in engineering, okay? Because if I want to start proof over proof over proof, then my lectures is going to be a little bit boring probably. So now let's talk about this important thing of, okay, now could you tell me where I can use any of these? Okay, sure, let's do that. So one of it is if you have the spring mass problem. So here I have this mass that is rolling on this surface. It is attached to a spring. There is no friction, rolling friction, Coulombic anything. The position of this mass is shown with letter X. There is no external force. You give it some initial condition of x of 0 equal x naught, and you release it from rest. So x dot at time 0 is 0. You are releasing it from rest. You just move it a little bit off equilibrium and let it go. You want to know what kind of motion x of t this object will experience. Well, as you know from pure intuition, right, or experience, it is going to start vibrations, right? It is going to oscillate. Now, how can I show this? Well, you draw the free body diagram of this guy, and the only force along the x is k times x. You also have mg and n. And you have your coordinate system. And then you write some of the equations along the x-axis. This is equal to mass times acceleration along x. And so you will get your governing equation that mx double dot plus kx is equal to what? 0. This is your governing ODE, and it is what? It is subjected to those two initial conditions. It needs two of them because the order is second order. Now my solution is, what is this x of t? Okay, if you remember from your differential equation course, whenever I give you a linear ODE like this with constant coefficients, so the coefficients are constant, they are not time varying. The coefficients are constant, the whole set of equation is linear. The homogeneous solution, which here is the only solution because the right hand side is 0, the solution here should be x of t is equal to a1 times e to the s1t plus a2 times e to the s2t, where s1 and s2 are the roots of what we call the characteristic equation or the auxiliary equation, which is ms squared plus k is equal to 0, correct? So you form what you call the auxiliary equation or the characteristic equation. And the roots of this are what? The roots are S1 and S2. So the question is, what's the solution here? ms squared plus k equals 0. So from here, clearly s squared is negative k over m. But you know k and m are positive entities here. So s squared is going to be negative. And there is no real solution for this unless we say this is equal to what? For negative 1 here, right? This is like negative 1. Negative 1, I write it as I squared. And this I write it as square root of k over m, the whole thing squared. I can write it that way, right? Because this is going to be k over m, this is going to be negative 1. And so the solutions are going to be S1 and 2 are what? Positive and negative. Square root k over m times I. Okay, so these are the solutions. Square root k over m times I. These are my solutions. Where now, if you don't mind, I would just call this guy here omega n, which I call natural frequency of the system. We'll talk about it. But if I just call it omega n, then my solution x of t is going to be a1 e to the omega n times t, I, omega n I times t, plus a2 e to the negative omega n I times t. So that is my solution. Now, what is a1, what is a2? We have to find them from the initial conditions. So here I say x of 0 is x naught, so let's plug that in. X at time 0 is what? If I plug in 0 in any of these exponential, the result is 1, so it is going to be a1 plus a2. This is equal to x naught, and then x dot at time 0 is going to be, if you take time derivative, the term omega ni gets out of the exponential, and then the exponential at time 0 is going to be 1 again, so it is going to be omega ni. This one is going to be minus a2 omega ni is equal to what? 0. True? So here I plugged in, because again, here, let me take derivative for you for clarification. So clearly here, the derivative x dot of t is equal to a1 omega ni e to the omega nit minus a2 omega ni e to the negative omega nit. And now if I plug in 0, the exponentials are going to be 1, and you will get this. Now from here, since omega n and I are non-zero, clearly the only solution is a1 equals a2. And if I plug this up here, since they are the same, it is going to be 2a1 equals x naught. So from here, a1 is equal to a2, and it's equal to x naught over 2. Okay, so these are those two unknown coefficients that I found through initial condition. And now I'm going to plug them back into my equation for x. Let's see what I get if I do that. So if I do that, now I will get x of t to be equal to, both of them have x naught over 2, so I write it, and then it is going to be the addition of those two exponentials. So this is going to be omega n I t, and this is going to be plus e to the negative omega n I t. Agree? Now, here I use the Euler formula. I use this important Euler formula that we had here. And if I do that, then it is going to be what? It is going to be x naught over 2. The first term is cosine of omega nt plus I times sine of omega nt. The second term is going to be, I use a different color, cosine of negative omega nt plus I times sine of negative omega nt. Agree? And what you know from cosine and sine, cosine is an even function, so this is the same as cosine of omega nt. It doesn't matter if you negate the argument. But this one is an odd function, negative comes out. It is going to be negative sine of omega nt. And now these sine components will be eliminated, will be simplified. The cosines will be added to 2 cosine. That 2 with this 2 will simplify. You will get x naught times cosine of omega nt. So this is your solution. The response of the system is a harmonic function. So it is going to oscillate, right? Where x naught is the amplitude of your oscillation and omega naught is what? The frequency of the oscillation. Correct? So this guy is, let me write it for you. This is the amplitude of oscillations. Now I don't know why the font size is this small, but we can change that for sure. And make it like 120. There we go. So this is the amplitude of oscillation, and then this is called the frequency of the oscillation. And we call it natural frequency because it is happening, it's an oscillation that is happening without any external force. It's how the system will oscillate by itself. So this guy, which was the square root of k over m, we call it what? Natural frequency of the system. Okay, but clearly the system will exhibit oscillations with magnitude x naught. Correct, so this is x naught here. This is negative x naught. And the period of the oscillation from here to here, if you call it t, this t is equal to 2 pi over omega n. Okay, so this is x versus time. Clearly, the system will oscillate. So you see here, I use complex numbers, complex solutions, an Euler formula, and I easily showed you that the solution should be a harmonic response. Right? That's one of the cases that I use a complex number or system of complex numbers in a physical problem. Now you might say, do you know anything else? For sure. Now you can look at an electrical system if you want, and you can solve electrical systems with complex numbers too. So let's say here I have an RL circuit, right? Or LC circuit actually, or RLC circuit. So here is my input voltage, and it goes to an inductor, it goes to a resistor, it goes to a capacitor, and it comes back. Okay, so this is L, this is R, this is C. The current in this series circuit is I, and that's why you want to use what? J instead of I for base of complex number, and this is positive and negative, right? Now, if somebody tells you what is I of t, if I give you Vn of t as a function, L and R and C are known, can you give me I of t? And if you know from your electric circuits, the voltage across each one of these elements, when added together and then added to Vn, should be equal to 0, right? Some of the voltages across the loop is equal to 0. That's called Kirchhoff's voltage law. And that is like Vn minus the drop over L, which is L di over dt, and minus the voltage drop across the resistance, which is R times I, and minus the voltage drop across the capacitor, which is 1 over C integral of I dt. This should be equal to 0. Okay, so this is your governing equation. And here, what you can do, you can take a time derivative from this. And it is going to be V dot of n, whatever it is equal to what? L second time derivative of I with respect to time plus R times first derivative of I with respect to time plus 1 over C times I. And clearly, if you look here, this is a second order differential equation in terms of I. It is linear, the coefficients are constant, but it is non-homogeneous. So the solution I of t will be a homogeneous solution plus a particular solution. The particular solution depends on this function v dot of n, how that kind of function is. The homogeneous solution does come from, again, what? It does come from the auxiliary equation, correct? So if I right now just focus on IH of t is equal to A1 times e to the s1t plus A2 e to the s2t, where s1 and s2 are the roots of the auxiliary equation L times s squared plus R times s plus 1 over c is equal to 0. Okay, these are the roots of this characteristic equation, which directly comes from the right-hand side. Now, clearly, if you solve here for s1 and s2, this is a quadratic. So s1 and 2 are going to be negative r plus minus square root of r squared and then minus 4 times L times 1 over C divided by 2L. And now the solution here does depend on this guy under the square root. If this guy is negative, then you will have a what? You will have a complex component. Something times I comes out of the square root. And your roots are going to be what? Going to be complex. And so it means, again, you have to plug in complexes here and plug in the initial conditions to find A1 and A2. And then what again? Yes, try to use Euler formula and simplify it down to a real function. Now, the important thing is this: when you're trying to solve something like this, keep in mind that the ultimate solution for the current has to be a real function. If when you do all of this, you end up with the solution, let's say harmonic or whatever it is, that has I in it, so your final solution for this homogeneous component at the end of the day has I in it, there is somewhere that you made a mistake. If you see here, although initially I have I in these terms, but when I applied initial conditions and simplified, there is no I in my solution, because remember, I's are imaginary. This is a physical system with a real solution. The X does move, and the motion of that is not imaginary. It can be measured. It's a real number. The same thing here, that the electric current in this circuit is going to be some real number that you can measure with an amp meter, okay? With a current meter. It's not an imaginary number. So you need to keep in mind that however you do it, there is a relation between this A1 and A2 that allows you to simplify. And that is not super hard to see, that if you have these two roots, S1 and S2, from here you clearly can see if, let me tell you this important thing, if this R squared minus 4L over C is negative, then it means your complex numbers S1 and S2 are going to be what? Going to be complex numbers. But since this is like, let's say negative 9 times, it's like negative 9, okay? The square root of negative 9 is plus minus 3 times I. So one of your roots is negative R plus 3 times I over 2L. The other one is negative R over 2L minus 3I over 2L. So clearly, if the quadratic equation has complex roots, the roots have to be what of each other? You're right, they have to be complex conjugate of each other. And then, if your solution is real, which in this case it has to be, you can easily show that if S1 and S2 are complex conjugate of each other, then A1 and A2 should also be complex conjugate of each other. Otherwise, your IH of t will have imaginary components in it. If IH of t has to be pure real, this condition has to be what? This condition has to apply, and you can see it here as well. That if you look at this A1 and A2, they are the same, but they are real. When two numbers are real, they are of course conjugate of each other because there is no imaginary part. But clearly, in this case, you can say they are also what? Conjugate of each other. Each real number is its own conjugate, right? So this is an important thing. And then, as I said, you have to resort to complex numbers to solve it. So just keep that in mind. That is very important. Good. Now, let's talk about a few more things here. And that is the polar form of complex numbers. Let's talk about that as well. And then We can talk about the roots and so on, the powers, some functions, derivatives, and so on. So first thing first is the polar form of the complex numbers. So that clearly comes from the definition of the use of this Euler equation, right? Because if you remember, one way I can show my complex number, or the only way that I have learned so far, is using the real part and the imaginary part, right? So if this is the imaginary axis, and this is the real axis, and this is my complex number z, which I showed by the real part and the imaginary part, let's call it a and b in this case, so it is a plus bi. That's one way to show it. Another way is if I show it using its magnitude, let's call the magnitude of it r if you don't mind, and the angle or argument of it, which is theta. Okay? Using polar coordinates, you know, based on what we defined for the magnitude and the angle, r is clearly the square root of a squared plus b squared, and theta is equal to tangent inverse of b over a, correct? That's what you know. Or you can also say that a is r cosine theta and b is r sine theta. So now the complex number z, which was a plus bi, can be written as r cosine theta plus I times r sine theta. And if you factor out r, it's going to be r times cosine theta plus I times sine theta. And guess what this guy is? Yes, you're right. That is exponential of I theta. So from here, you can also write your complex number as r times exponential of I theta. And this is the new format that you can use to show the complex number. So the complex number can also be written as its magnitude times exponential of I times its angle, instead of its real and imaginary part. This format of showing complex numbers is what we call polar format. And using this format, many times when you want to especially multiply, divide, and raise to a power of a complex number, it is way more convenient. So let's say I want to multiply z1 by z2, where z1 is written as r1 exponential of I theta 1, and z2 is written as r2 exponential of I theta 2. Well, we easily know that r1 times r2, they are the two numbers that you multiply, and the exponentials, when you multiply, their powers are added. They both have I, which you can factor out. So this is going to be theta 1 plus what? Theta 2. So the product of two complex numbers is what? Another complex number, where the magnitude of it is the product of the two magnitudes, the angle of it is the addition of the two angles, right? So it's, to me, way easier to add the two angles and multiply the two products than to apply four operations here, right? AC minus BD and AD plus BC. Okay? So it depends on how you want to show it. Or when you are trying to divide z1 by z2, it is going to be r1 e to the I theta 1 divided by r2 e to the I theta 2. And all you need is to divide r1 and r2. And the exponentials, their powers will be subtracted. You see? So the magnitude is the ratio of the magnitudes, and the angle is the subtraction of the angles. Again, to me, this is easier than basically applying all of these calculations to get the division. Okay, so it does depend on what you want to do, but definitely for multiplication and division, this polar format is easier than the real imaginary. For addition and subtraction, the form of imaginary and real is easier, because you can easily multiply and divide exponentials, but when you want to add and subtract them, it's not that easy. And the better power of this is when you want to raise a complex number to a power n. So now this is r e to the I theta, the whole thing to the power n. So r will be raised to the power n, and exponential, when it raised to the power n, you know that n will come and multiplied by that, so it is going to be I times n theta. Therefore, the magnitude is going to be r to that power, and the angle is going to be n times the original angle, right? So this is very good. As I said, you want to raise a complex number to the power 4, 5, 6. I would always write it in the polar format, then I raise it to the power. Because let's say, I say, for example, z is equal to like 2 plus 3 times I. And now I ask you, what is z to the 5? Well, I don't expect you to do this. Because it takes forever to apply, do the distribution, simplify. It takes forever, right? So what I expect you to do is this. Now let me make this 3 a little bit easier. Let's just, for the sake of fastness of the calculation, I say 2, if you don't mind, because the angle of this is not going to be as, or well, that's fine, let's just use 3. Let's not avoid it. So if I want to write this as magnitude and angle, I have to find a magnitude and angle. So magnitude of it is clearly r. That is equal to square root of 2 squared plus 3 squared. And the angle of this theta is equal to tangent inverse of 3 over 2. So let's calculate these numbers. And as I said, this is not a good strategy to use the distributive property and keep multiplying. Okay, that's not a good strategy. I don't recommend you ever do that, especially when the power is more than 2. So clearly I can easily calculate them. And by the way, here is the good part to use MATLAB. So if you have complex numbers, how would you work with them in MATLAB? So here I define a complex number, say z equals 2 plus 3 times I. Whether you say 2 times 3 times I or 2 plus 3 times j, the result is the same. For MATLAB, I and j are both base of complex numbers. You can use either one. And now, one of the commands you can do is ABS. ABS gives you the angle, so you say, what is the absolute value of z? That is the magnitude. Clearly you can see, if I want to use 2 decimals, it's 3.61. And then you're going to calculate the angle, and try to use the angle written in radians, not in degrees. Although if you keep attention and you know what you're doing, it's okay if you want to write it as degrees, but I always prefer to write theta in radians. And so that's where you have the command angle, if I'm not mistaken, of z, and this is the angle theta, and it is in radians, 0.98 in radians. Okay, so it is 0.98 radians. So now I can write my z as 3.61 e to the 0.98 times I times theta. And so when I want to raise z to the power 5, I raise this 3.61 to the power 5, and I multiply this angle theta by 5 times. And you know, 5 times that, if you want, you can write it that way, that's okay. And that's the result, done. Okay, instead of, because you know how many terms you will get here, right? This is 2, 2, 2, 2, so you will get 32 terms when you expand it. And then you have to simplify all sorts of powers of I from power 1 all the way to power 5. Simplify, form, add them together to get the result of this. Okay, and now if you want to write this in terms of real plus imaginary part, no worries. Just multiply this by cosine of that angle, correct? And then multiply this by sine of the angle to get the real and the imaginary part. So it is always easier to do that. By the way, in MATLAB you have the command real of z, and you have the command image of z, which will give you the real and the imaginary part of a complex number. You also have the command conj, if I'm not mistaken, and that gives you the conjugate of the complex number. If you want to raise z to the power 5, all you need is this. Okay, so it is 122 minus 597 times I. That's the result. Okay, so if you write this in terms of image and real part. Okay, so I told you some relevant MATLAB commands: the absolute, correct, for magnitude, angle for theta, real and image, and for conjugate. And you can do anything you want with that. So these are the very base of complex numbers that you learned. And this is good. One last thing. Maybe I want to tell you, and that is the nth root of a complex number. Okay? Because to the power 2, 3, 4, 5, there is no problem. It's just the nth root of a complex number that I guess it is, for me, very important to mention that to you. So the nth root of a complex number, how would you calculate that one? Let me tell you. So if I have a complex number z, which is written as r to the e I theta, and somebody says, what is the square root of z? Well, you know, this is the same as z to the power 1/2. And 1/2 is like the previous case of power, where n is just 1/2 instead of 2, 3. So this is going to be r to the 1/2 times e to the I theta, but theta should be also multiplied by 1/2. Okay, so it is going to be square root of r times e to the I half of theta. Correct? That's what you expect for the, let's say, square root of a complex number. Split the angle in half and take a square root of magnitude. Now, the thing is this. A complex number in general does not have one nth root. It has n nth roots. Okay, what do I mean by that? Let me tell you that part. So, and that comes from this important property that this exponential function times I theta is a periodic function. What do I mean? So it comes from this important property, that what is e to the I theta plus 2 pi? What is this? If I add 2 pi to the argument of this function e to the I theta, what happens? Well, this is going to be cosine, correct, of theta plus 2 pi, and then plus I times sine of theta plus 2 pi. And you know, sine and cosine of any angle plus 2 pi is the same as the cosine and sine of that angle itself, because these functions are periodic with period of 2 pi. So this is going to be the same as e to the I theta. So you see, adding 2 pi to the argument of this function will not make any changes. So we say f of theta equals e to the I theta is periodic, correct, with a period of 2 pi. Okay, good. So now let's look at this. What about this function? E to the I theta over 2. How much should I add to theta so that the result of this reevaluation of this function will be the same as the original one? In other words, this guy is also periodic, but with what period? Well, all you need here is, instead of theta, you add what? Theta plus, what do you need? Remember, what comes out of here should be theta plus theta over 2 plus some 2 pi. If you add that, then the result is going to be what? The result is going to be the same as theta over 2, correct? Yes, so what I really need to add here is 4 pi. If I add 4 pi to theta, then this function is going to be theta over 2 plus 2 pi, which is going to be the same as original one. So this function is periodic with period 4 pi. On the other hand, if I do this function, 2 theta or 3 theta, let's say, now what? Again, all I need is this whole thing has to be like this to make it happen. And for that, since this 3 is there, I can factor this 3, and it becomes theta plus what? 2 pi over 3. If I only add this much to theta, then I will get an extra 2 pi to make the function periodic. So what's the period for this function? It is 2 pi, but what? Divided by 3. So in general, if I have the function e to the I n theta, whether n is bigger than 1 or less than 1, the period of this function is 2 pi divided by n. Now, if n is bigger than 1, you get like 2 pi over 3, 2 pi over 4. In this case, n is 1/2. So there's going to be 2 pi over 1/2, which is 4 pi. Okay, so this function in general, this function exponential of e to the I n theta, this function is periodic with period of 2 pi over n. Okay, good. So now look at this. Let's go back to this taking the nth root. When I say, what is the nth root of z? Okay, so here I say, well, assume that the solution is r, or what, z naught, whatever you want to call it. The solution is z naught. What does that mean? it means that z to the power n is the same as z naught. But what is z to the n? If z is written itself as r e to the I theta, then z to the n means r to the n e to the I n theta. This is equal to z naught. And let's write z naught also as r naught e to the I times alpha, if you don't mind. I write the argument of that as alpha. So this is going to be r naught e to the I times alpha. Good? What do you get from here? Well, from here, you clearly see that r should be square root, the nth squared of r naught. So that's the magnitude you need for the solution. What about the angle? This n theta should be equal to alpha, or since this function is periodic, if I add 2 pi over n to it, the result of this exponential is not going to change. Because this guy, as you know, is e to the I n theta, that is the same as e to the I n times theta plus 2 pi over n. Right? The result of this one and this one are the same thing, because here you get an extra 2 pi. So now I can say that this n theta plus 2 pi n should be the same as what? Alpha, right? Is that correct? Yeah, that's what you have, right? If that is the case, what does it mean about theta? Theta is what? Theta is going to be two pi k plus alpha divided by n, where k can be 0. If I plug in 0 in it, it is going to be what? Simply alpha over n, which definitely works here. It could also be what? It could also be 1, 2, and all the way to n minus 1. Any of these would, when it raised to power n, they give you 2 pi extra angle, 4 pi, 6 pi, 8 pi, 10 pi extra angles. And since when you take sine and cosine of that, the result is the same, then there will be no difference. So in general, the nth root, the magnitude of it comes from the nth root of the magnitude of the right-hand side. The angle of it comes from 2 pi plus k, 2 pi k plus alpha over n. K goes from 0 to n minus 1. So it means how many different angles would work in this equation? N of them. You clearly see k has n values. In other words, there are n roots, n different complex numbers would match this equation. And to make it simpler to you, I start with something very simple, and then I'll show you one more example. But let's say my question is this: what number, complex number, if you square it, the result of that will be 1 or -1? Well, you all know the solution is plus and minus I. I know that, correct? But just to go based on this formula, if I want to write this as polar format, I should write it, if you remember, when I did that famous equation in complex numbers. Where was it? That I showed you that favorite formula of mathematicians here. -1, you can write it as e to the I pi. Okay, so I write this e to the I pi, and magnitude of it is clearly 1. So now, from here, your z should be magnitude of it is square root of 1, and angle of it is what? What can you raise to the power 2 to give you pi or pi plus 2 pi? So one of it is pi over 2, clearly. When you raise this number to the power 2, e to the I pi over 2 is going to be e to the I pi. The other one is square root 1, but e to the I times pi plus 2 pi over 2. And you know pi plus 2 pi is 3 pi divided by 2 is 3 pi over 2. When you raise this guy to the power 2, the result will be 3 pi. And 3 pi, the cosine and sine of 3 pi are the same as cosine and sine of pi. So both of these are the roots, the square root of that. And what is e to the I pi over 2? Well, if you know, e to the I pi over 2 is cosine of pi over 2 plus I times sine of pi over 2. Cosine of pi over 2 is 0, sine of it is 1, so it is going to be I, 1, so it is going to be I. That's what I expected. What about this? This is going to be 1 times cosine of 3 pi over 2 plus I times sine of 3 pi over 2. And you know 3 pi over 2 has a cosine of 0 and a sine of -1. So it is going to be negative I. And that's what we had, right? We know if a square of a number is -1, then the solutions are I and negative I. So this complex number has 2 square roots. Now you might say, what about the cubic root? If I had the cubic root, like z cubed is equal to something, then what? Correct? Then what? For example, z cubed is equal to -1. What's the solution here? Well, if this was only in real numbers, there was only one solution. The solution was -1. But in complex numbers, you have more than one solution. You say, well, again, this guy is 1 times e to the I pi. Therefore, my solutions z1, 2, 3, there are 3 solutions, are equal to the cubic root of 1 times e to the I, and for angle, it's going to be this angle plus 2 pi k divided by n, where n is 3. And here you let k go 0, 1, and 2, where 2 is 3 minus 1, n minus 1. So what are the solutions are going to be? They are going to be 1 times, if I plug in 0 here, it is going to be pi over 3, so it is going to be e to the I pi over 3. That's the first solution. The second solution is 1e to the I. Plug in 1 here, that's going to be 2 pi, 3 pi, 3 pi over 3, that's pi. And finally, you have 1e to the I. Plug in 2, that's 5 pi over 3. So all of these numbers, when you raise them to power 3, the solution is going to be -1. You don't believe me? I'll show you. But here, just remember, this guy is -1. That's your real root. But there are 2 complex roots as well. These 2 complex roots, when you raise them to power 3, the solution is what? -1, and I'll show you. So here, your first number, z1, is 1 times exponential of what? I times pi over 3. So that is this complex number, 0.5 plus 0.866i. The other one is z2 equal -1, which is obvious. z3 is this guy times 5 pi over 3, which is like the complex conjugate of the original one. And now, if I say z1 to the power 3, look, it's -1. If I say z3 to the power 3, it is also what? negative 1. Pay attention that the imaginary part is 0. So 3 complex numbers. Again, one of them is negative 1. This one was 0.5 plus square root 3 over 2i. This one was 0.5 minus square root 3 over 2i. All these 3 numbers, when you raise them to power 3, the solution is negative 1. So in general, a complex number has n, a complex number z has n nth roots. Okay, if you want the 4th root, then there are 4 solutions. If you want the 5th root, there are 5th solutions. And there is a way that you can graphically also show them, and the graphical method of showing it is this. That, as I said, if the z to the n, if z to the n is equal to a complex number z naught, where z naught is r naught square e to the I alpha, okay, then the solution z, as I said, is going to be the nth root of r naught times exponential of I times alpha plus 2 pi k over n, with k being 0, 1, 2, all the way to n minus 1. A way to show it is graphically this. So they say the nth roots, or the nth solution here, are on a circle, where the radius of the circle here is square the nth root of r naught. That's the radius of that circle. And then the angles, so here I'm showing those roots in the polar format. Okay, so here again I'm showing those n roots in a polar format. So that's the radius of the circle all of these nth roots are on, and then the angles are, so the angle of first one is here, alpha over n, so that's your first root, where this angle is alpha over n. Then each 2 pi over n, you have another one. So this angle between each 2 roots is 2 pi over n. Okay, so these are the roots of the complex number in general. So in this case of this negative 1 that I mentioned to you, since this number, the magnitude of the right hand side is 1, already the roots should be on a circle with radius of 1. The angle was pi, so the first angle should be pi over 3, or 60 degrees, which is here. The next one is going to be 2 pi over 3, or 120 degrees, which comes here, and the other one comes here. Okay, where again this one was 60 degrees, this is 120, and this is 120 to here, of course. From here to here, this guy is 120 as well. So this is also 60. So the three roots are on that circle, and if you look at them, this is 0.5 plus square root 3 over I. This is 0.5 minus 3 square root 3, square root 3 over 2 I, and this is negative 1. Okay, so these are the nth root of a complex number. Now here I would like to stop this video as it's getting long, and I'll continue the rest of this video in a separate, the rest of this topic in a separate lecture, separate video. Thank you.